bass louder remix.
Welcome to video 9.4 covering gas stoichiometry. This video is going to bring stoichiometry back into our classroom. This video is going to help you understand the relationship between the mole and volume of gas. It's also going to talk a little bit about the standard temperature and pressure concept. And lastly, we're going to perform stoichiometry calculations based on the ideal gas and our mole volume that we see. So as we get started, make sure you grab your periodic table, your mole map, and of course your notes. So molar volume. You already know that when I look at the chemical equations, these coefficients here give me a mole ratio. So we already know coefficients give us a mole ratio. But when we're dealing at STP, when we're dealing at standard temperature and pressure, that is again at 0 degrees Celsius and 1 atm, or if we're working in Kelvin, 273.15, when we're dealing at STP, that these mole ratios can now be turned into liter ratios. So here's a calculation or a chemical equation for the Haber process on how to make ammonia. And what you see here is that if you have 3 moles of hydrogen gas and you react it with 1 mole of nitrogen, you can make ammonia. However, because we can work at STP, and because now the mole ratios are now volume ratios, we can simply say 3 liters of hydrogen gas will react with 1 liter of nitrogen. So it just makes it very simple and easy with our conversions. And I showed you that on the last video of where you use the ratio of 1 mole of any gas equals 22.4 liters. So again, this is a conversion factor you can use at any time, and we'll see that again here in a second. So again, my STP, 1 mole of gas equals 22.4 liters. This is my new conversion factor I can use, and it can easily help us do chemical reactions. Instead of dealing moles, we can now deal in liters of gases at STP. So as we get into stoichiometry, this is going to get a little bit tricky. It's really just doing what we've done before stoichiometry-wise, but we're going to add in a curveball every now and then where you have to use your Pivner equation or your ideal gas. So like always, I think it's a really good idea to start by labeling what they give you. And then again, as you start working through here and as you start looking at what they give you, you're going to have to decide whether or not to use the ideal gas law first and then stoichiometry, or just do stoichiometry and then come back to ideal gas law. This little picture here is just a reminder of your mole map, but go ahead and grab your mole map because you're going to be more familiar with it. So here we go. Our first problem here. So what volume does 0.0645 moles of gas occupy at STP? So I'm only given one thing here, and this is our N, and we're given our STP. But since I'm seeing it as STP, I should automatically start to be thinking that 1 mole equals 22.4 liters. Knowing that's a conversion factor, I could use it any time. And I see that I'm just simply trying to find a volume for moles. So I can do a simple conversion problem of just say 0.645 moles. I'm going to write down what they give me. Step 2, I'm going to follow those units. And step 3, I'm going to get my conversion factor, which is simply going to say 1 mole equals 22.4 liters. So you put that in your calculator, and it comes out to 1.44 liters. So if I was looking at my mole map, that's simply saying that I'm starting in moles, and I'm going to convert to liters. So again, on your mole map, you can go ahead and add this in. 22.4 liters is your conversion. This is called the molar volume. And again, this is only true at STP. All right, so let's look at the second practice problem we have here. What volume of NO2 gas is produced from the combustion of 100 grams of NH3, assuming the reaction takes place at STP? So again, once you see the STP, don't forget you have that 1 mole to 22.4 liter conversion there. And we're simply going to, again, follow our stoichiometry. Looking here again, since I'm at STP, I can use this conversion factor. And so now I'm seeing that I'm going to be starting in grams of one thing. I'm going to need to go to liters of something else. So again, as I look at this, notice I'm going to be starting in grams of one thing, and I want to go to liters of something else. So start here, follow your mole map all the way down to here. And again, this would just be that 22.4 liters. So what do? Step one, write down what you know. Step two, follow your units. If I have grams of NH3, I have to have grams of NH3 down here. If I look at my periodic table and if I add up the mass of my nitrogen and my hydrogen, we're going to see that 1 mole of NH3 equals 17.04 grams. Now I just converted from here to here. I got to keep going. Now I'm going to convert from 1 mole of one chemical to 1 mole of something else. That's called the mole ratio, and we just simply use our coefficients. So if I go mole of NH3, and I'm going to go from mole of NH3 to mole of NO2. And then how do I get that conversion factor? I just see it's a 4-to-4 relationship. And then again, follow my units, mole of NO2. And now that I'm in mole of NO2 and I want to go to volume, I simply use that conversion because I am at STP. So just simply say 1 mole of NO2 is 22.4 liters of NO2. And then, of course, we hit our equal sign. If you put that in your calculator, you come up with 131 liters of NO2. So again, same thing we've been doing. We just added another conversion problem here, conversion factor. But again, write down what you know, follow those units, and just know that I can ask you a variety of questions based upon these conversions. All right, so the last question we have here is where you have to, again, have an understanding of stoichiometry, but yet also have an understanding of the ideal gas law. So when I go through here, I'm going to read that it asks me how many liters of NH3 do I want. So I'm looking for volume of NH3. And we want to say that can be produced at 27 degrees Celsius. So this is my temperature. And you already know that that probably needs to be converted to Kelvin. So you just add that to 273.15 K. And if your pressure is given, your number of moles is given. But here's the problem. I have number of moles of nitrogen. So I have moles here, and I want to go to volume here. So again, I like to go ahead and label things up here. And then we're going to call this a decimal there to make it 2 sig figs. And I want to go through volume of NH3. So since I am not at STP, I cannot just use my conversion here because I'm not at STP. So what I have to realize is I have to use a combination of stoichiometry and my Pivnert equation. So first of all, if I want to find Pivnert, because it gives me, I'm looking for a V and it gives me a T and a P and I can cut my own R, I have to find the N, but not of nitrogen. I have to find my N of NH3. So what we're going to do is do a conversion problem to go from here to here, or in other words, we're going to go from here to here by simply saying 20 moles of N2 is, follow your units, and I can see that I can convert from mole of N2 to NH3. That's simply a 2-to-1 ratio. Now that is going to give me 40 moles of NH3. So now I have my pressure. I'm looking for my volume. I have my number of moles. I have my temperature. And of course, we have R constant memorized or easily available. So now from this point, we're just going to go back into our ideal gas equation. Since I'm solving for volume, my equation is going to look like this. Now I'm going to start to plug my numbers in. I have 40 moles of NH3. I need my R value, which is 0.0821. It's going to be liters atmosphere over mole K. I have my temperature, which was converted already to Kelvin. And then I got my pressure, which I could write 760, but looking ahead, I cannot have it in torr. I have to go ahead and put that into ATM. So if you remember, 760 torr equals 1 ATM. So I need to go ahead and throw that in there. And that, of course, is why I love you putting your units in here so you can make sure everything is canceling out. And I see here that moles cancel out, ATMs will cancel out. So Kelvin will cancel out. I'll be left in liters. Put that in your calculator, and you come out with 985.69 liters of NH3. And if I said I had 2 sig figs here, then that would actually bring this number down to 90 liters of NH3. And that would be the answer I am looking for. Unit and chemical. So as you can see, nothing too terribly over the top. It is just a few spots where you got to pay attention to your mole map and throw in the ideal gas equation every now and then. With some practice, though, I think you can get this. So again, long story short, if we're dealing STP, there are 22.4 liters in 1 mole of gas. And we can use gas stoichiometry problems by using also the ideal gas law, and we can answer all kinds of conversions or chemical-based equations. Have a great day.